Let's wait for a couple more minutes for people to join and then we'll get started. Okay, let's get started. So, welcome to the week 3 live session. Hope you can hear me and see my slides clearly. If not, drop a message on chat. But yeah, I am Prashanti SK. I'm a PhD student at IIC Bangalore and I'll be handling today's live session from 6 to 7. So, for people who are joining this live session for the first time, I have a sort of an introduction slide here as to what you can expect. People who have already joined them the previous week and the week before will be familiar with this. So, yeah, nothing new here. So, you have 3 of these live sessions every week. Okay, let's wait a minute more since people seem to be joining and I don't want to have to repeat content again. Let's just wait a minute more. Okay, so going on to what you can expect from these live sessions. So first of all, there are 3 of these every week at different times and different days. So you can check your course announcements page to find the meeting link. You also get reminders on email. And these are sessions supposed to be focused on problem solving so that they will help you with your assignments. So you might have seen 2 or 3 assignments by now, and the questions discussed in these sessions will be very similar to the assignment problems that you have. So you'll get an idea on how to think and how to solve those questions, but we will not be solving any questions that are the same as your assignment questions. They'll just be very similar. The other thing is that if you have any doubts from that week's content or the previous week's content, you can post your questions on chat and I'll take up those questions. I'll also pause twice or thrice in the session to see if you have any doubts on the previous week's content, right? And during every question, I will ask for answers and you can feel free to post whatever option you think is the correct one on chat. So it doesn't matter if your answers are right or wrong, right? The purpose of doing that is to make it interactive so that I get an idea of what you guys are thinking. Suppose a bunch of people have say confusion between two options, then I know that that needs more explanation and I can focus on that. So it helps me fine tune what content I am telling you about each question, right? So I would request all of you to interact as much as possible. And similarly, if you have a doubt in any explanation that I am giving you, feel free to post those questions also on chat. I will pause after I discuss each question to see if you've understood it or you need some clarifications. So generally questions are through chat and not unmuting, because it gets difficult to handle when there are multiple people. And you will be getting slides as well as recording post the session, and that will be there on the announcements page of the course. So hope this clears up everything about these live sessions. If you have any questions on these logistics as well, you can post them on chat right now. So I'll wait another 30 seconds before I move to this week's content. And for people who just joined, this is just going through what each live session consists of, in case you haven't joined one before and this is the first one you're joining. If not, you're already familiar with this, so nothing new. Great. So let's move on. And so just to give you a kind of overview on what the lectures covered this week, which you anyway would know if you've watched the videos, right? So we looked at some of the OS design stuff. Okay, there are multiple people joining. Please try and join, let's say around 6, 5:59, something like that, because if you join in the middle, you lose context of what I'm saying, and then I'll have to repeat certain things. So yeah. Anyway, so this is just going through all the things that you guys have seen in week 3. So the design of an OS, we looked at things like modules, the microkernel based approach, the layered approach, and then the major topic that was focused on was processes. So we looked at everything from the structure of a process, what is the state of a process, what is a process control block, what are threads, how do you schedule these processes, and scheduling queues that you have to help with this scheduling, things like context switch, process creation, termination, things like that, right? So your assignment for week 3 and the questions that we will be discussing right now will focus on these topics. So let's move to the questions. So here's how we'll do it. I'll read out the question and the options, and I'll look for answers on chat. I'll wait a little bit so that I can see what you guys are thinking. And then we'll discuss the answer to the question. And I'll again pause to see if you have any doubts on the explanation. Okay. So let's start with the first question. A program becomes a process when A. The program is stored on a disk as an executable. B. The executable file of the program is loaded onto the memory. C. The process replaces the program which was stored on the disk. D. None of the above. So this question is focusing on the difference between programs and processes and what is the transition between it. So what do you guys think is the answer? Please type it out on chat. As I said, it doesn't matter if you're wrong or right. I'll wait 30 seconds. Any answers? When do you think a program becomes a process? No answers? Let me wait another 10 seconds. Okay, let's take a look at the answer. So the answer is the executable file of the program is loaded into memory. So that's when a program becomes a process. And I think you've had content on this in the course. So essentially you can relate to this very well, right? So let's say I'm sure all of you or most of you have written C programs that do things like maybe a matrix multiplication, maybe a simple addition, maybe just printing out hello world, right? So you write a program and then you save that on your hard disk, and that is stored. Maybe you even compile it and you store the executable, right? But it becomes a process, as in it's actually running once you run that executable, and the executable is loaded into the memory. So that's the key difference between these two terms, a program and a process. So when something is running, we term it as a process, whereas when you've just stored something on disk, when you've stored an executable on the disk, then it is just a program, right? So this is why B is the right answer, and A is the program is stored on a disk as an executable. So at that point it is not yet a process, it is still just an executable on disk, right? And C is the process replaces the program which was stored on the disk. That is not the case, it does not replace it, it is just loaded into memory so that it can now start to run, right? So that's the answer. Any doubts on this explanation, any information that you need, any clarifications that you want, post it on chat. I'll again wait 30 seconds before moving to the next question. And here's where you have interesting things, right? So let's say you have Excel, right? And Excel is now, it's a program. And then let's say you open a certain worksheet and you start doing some operations. So that is a process. And let's say you open another worksheet and start editing, that also in parallel. So you have two processes which are using the same program Excel underneath, right? So you have, so this is why it's important to understand this difference in terminology between a process and a program. So any confusion on this? So for people who just joined, we are discussing questions and this is the first question. So I'll pause another 10 seconds to see if you have any doubts on this option or if things are clear. Okay, I'm guessing things are clear. So let's go to the next question. Again, this is a very simple question and it closely follows the previous question. So I'm sure you'll be able to guess the answers to this. So the question is, program is a dash entity and process is a dash entity. Your options are active, passive, passive, active, passive, passive, active, active. So what do you think is the answer? Please type it out on chat. Okay, B. B is program is a passive entity, process is an active entity. Great. Any other answers? Anyone else who thinks something else is the answer? Anyone else who thinks that B is the answer? Okay, let's look at the answer. So the answer is B. Program is a passive entity and process is an active entity. And I think the explanation was very close to the first question's explanation. In fact, this is the recap slide from your week 3's content, right? A process is a program in execution, and a program is just a passive entity stored on the disk as an executable file, whereas a process is active, and this re-emphasizes this. Program becomes a process when executable is loaded into memory. And yeah, this is another interesting thing. How do you actually execute something, right? So in the example that I was giving about Excel, you double click the Excel icon, the app icon, and the Excel opens. So that is a GUI mouse click mode of execution. Whereas you could have things on typically on Linux. Let's say I'm guessing most of you would have used Ubuntu, and you would have used commands like commands to just run a C process executable, or commands to list the files in a directory. Things like ls, or you might have run a bash script using bash and followed by the script name. So that is the command line based execution of a program. So you can start this execution via multiple things. And this is the other example that I was giving. One program can actually be several processes. So you can have one Excel as your program, but you can have multiple processes that are using the same program. Or you could have on a shared system. So let's say you have a machine in your lab that multiple people are logging into, right? And two different users might also be using the same Excel. So even in that case, you could have this one program being several processes. So these are some examples of processes and programs, and hope this clarifies both question 1 and 2. Anything else you want to know? Anything you're curious about? I'll pause for a minute. So you should kind of try and relate these definitions to things like the structure of a process, right? Now I said you have one Excel program and you have multiple processes that use the same Excel. So what are the things that need to be different between these two processes? What would be the things that are same between these two processes, right? So you would have looked at things like the code segment, the data segment, the text segment. So you should think about those things and try to relate this. So if I have multiple processes using the same program, which of those segments need to be different for the process to work correctly? Which of those segments need to be the same? For instance, both the Excel programs would be using the same code, but the variables that they might have might be different. So which of these sections should be the same? Which of them should be different? So those are things that will help you connect these concepts. So the two concepts being what is a process, what is a program, and the layout of a process in memory, right? Okay, if there are no questions on this, we can move to the next one. Any questions? Okay, let's move to the next one. Yeah, so this is talking about the process structure that I was just mentioning. So a process structure may contain A, heap, a memory that is dynamically allocated during process runtime. B, process stack containing temporary data. C, data section containing the global variables. D, all of the above. So which do you guys think is the answer? Which of these is relevant to a process structure? Please post your answers on chat. I'll wait 30 seconds. Okay, we have one answer, D, all of the above. Nice. Anyone else? Okay, D. Anyone thinks differently? Okay, let's look at the answer. So the answer is D, all of the above, and I think I have a recap slide here which will help you understand this, right? So a process is not just the program code, right? Because the code is something that doesn't change, but when you actually execute it, you have all these temporary variables, you have memory that is allocated at runtime, things like that, right? So it includes more than just the code. So it includes this text section. It also includes the activity, basically things like the program counter, things like the process registers. So why do you need these things? Now think about it, right? So let's say you're doing something on Excel, right? And then you decide to join this live session. So you switch to a Google Meet. So your processor has essentially switched from running your Excel workload to your Google Meet, right? And let's say after this live session, you go back and you try to do something on the Excel. So if it has to resume correctly, you would need the state of that process to be preserved. So things like the value of the program counter, which tells your computer where to start the execution again. And then processors registers, that also helps determine the state. So the registers all have some values while you're using this program, and when you switch to a different program, these registers are usually saved, and once you get back to your old program, then okay, once you get back to your old process, not program, the registers need to be restored. So this is a way of ensuring that you're able to continue your work without any loss of information. So this state of a process needs to be preserved, right? And this state also includes things like the stack, which has temporary data, things like function parameters, return addresses, local variables. It also has the data section, which is mostly global variables. And you also have a heap, which is memory that is dynamically allocated during process runtime. So this is broadly the process structure. Now going back to this question, so we see that heap is something that you need to have as part of process structure. Similarly, you need to have the process stack containing all this temporary data, and then the data section containing the global variables. So all of the above is a valid option here. So any questions on this? Any doubts? Something that's not clear? I'll pause for a while. Okay, since we're almost 20 minutes into the session, I'll pause once also to see if you have any doubts from the lecture content so far, right? You can ask any questions you have on chat. Some concept that you didn't understand, something that's not clear, something that you'd like more information. If there's anything, please post it on chat. There's also a discussion forum that you might have seen on the course page, so you can always post questions there. But these live sessions are meant to be interactive, right? If you have a question, you can get it cleared right away. So if you have anything, post it on chat. I'll wait another minute. I'll also ask this again towards the end of the session because people seem to be joining and leaving. So yeah. Okay, I'm assuming there are no doubts both on question 3 and on week 3 content. Great, let's move to the next question. So when the process is waiting to be assigned to a processor, the process state is called A, new, B, running, C, waiting, and D, ready. So this is again a question on the state of a process, right? So you would have seen all those transition diagrams from one state to the other and when a certain transition is triggered. So do you remember what the state is when it's waiting to be assigned? Any answers? Okay, A, new state. Okay. Anyone else who thinks it's A? Anyone else who thinks it's something else? Okay, D, ready state. Okay. Any other answers? Okay, let's look at the answer. So the answer is ready state, and let's look at this entire set of transitions once so that the concept is very clear to you. So the states that we have are new, running, waiting, ready, terminated, right? So new is when a process is being created, and running is when instructions are being executed. Waiting is when the process is waiting for something to occur, and ready is when it's waiting to be assigned to a processor, and terminated is when it has finished execution. So let's look through this state diagram, which will make it very clear, right? So you have a process that's being created, so it's in the new state here, and then it is admitted, so it moves into the ready state, right? And then so at this point it is waiting to be assigned to a processor. It has been created, it has been admitted into this queue, it's waiting for the processor to take it up. So think of it this way, so you are clicking the Excel icon, right? And at that point you might be doing something else, so the process will not immediately start running, although to a user, a human being, the delays are quite low, so you don't perceive it. So you don't see this delay between clicking the button and actually the process starting to execute, right? But sometimes when your system is very heavily loaded, when you have 20 things running and you try to open something, you might see this lag where it takes a few seconds to actually start running, right? So that then is this transition. But typically we don't see it because all of this, the processor is much faster than a human being, right? So you never see these delays, but this does happen every time a process is being created and it starts running. So it moves from ready to running as and when the scheduler dispatches it. And you would have learned things about CPU scheduling, saying there is this time slice. So when this time slice expires, that process will give up the CPU and the next one will be picked from this ready queue. You might have other scheduling mechanisms, right? For instance, so the scheduling is a very interesting area, and you should think about it in every kind of system that you see. For instance, you've learned about interrupts in week 1 and 2, right? And those are typically high priority events. So let's say you press a key on your keyboard, you can't be expected to wait 1 second for it to actually happen. So interrupts get priority. Similarly, you have real-time systems or systems where the criticality of the task is extremely high. So let's say you have an autonomous vehicle and it's doing something like pedestrian detection, and then it needs to stop because it's detected a pedestrian. Now that can't work this way where it has a time slice, and once that time slice elapses, this process of braking the car starts. It has to be immediate. So you might have some priority based scheduling then, saying that this task has the highest priority, so this task can preempt or interrupt any of the other tasks running. Or you might have a system where it's not so critical to keep things running. So you might have a very simple first come first serve, right? You would have heard of FCFS. So the process that comes in first gets executed first and the others wait, right? So these are all different scheduling algorithms that are available. But for now, you can think of this as a black box, as in the scheduler has some algorithm to figure out which process to move from ready to running. And it does that. And when it does that, the process is actually executing, the instructions are running. And then let's say some IO the process needs to do some IO, or there is some event which it's waiting for. So immediately it goes from running to waiting. And why is this done? So think about this at a higher level. Why do you need all of these states? Why do you need this transition? What is the point of scheduling as a whole, right? So the point of scheduling is to keep your processor busy. You want the utilization of your processor to be as high as possible. And why do you need this? To support multiple things running efficiently. So for instance, if when an IO event when your process needs to do IO, if I still keep it in the running state, it is just going to do IO and my CPU will be idle. At the same time, nothing else will run. So it's a very inefficient way of utilizing the system resources. So whereas according to this state diagram, when there is an IO or when your process is waiting for some event where it has nothing to run, it immediately puts it in the waiting state so that it can pick up something else and run it. So this is a way to use your system resources as efficiently as possible. So things like you being able to use say 20 processes at the same time, and not just 20, right? You might have a lot more. If you go look at, let's say, whatever operating system you're using, try this out today after the session. So let's say you're using Windows, open your task manager and look at all the processes, not just the user processes, but the system processes, the background ones, the services, all of which are running. Similarly, if you're on a Linux based operating system, you can look at PS, which lists all processes. So there are so many of these running at any given point, and that's why it's important to have these states so that you can utilize your hardware efficiently and at the same time have a very good user experience. Ultimately, if you use your machine and feel that, oh, it's really slow, then that's not a good experience for you as the user, right? So the operating system design has to be such that the user experience is good and the hardware is utilized to its fullest. So anyway, we were at IO or event wait. So it goes into that waiting state and it waits till this IO is completed or till this whatever event that it's waiting for happens. And after that, it is put back into the ready queue. So when you see this diagram, right, think about why the transitions are like this. For instance, why can't you go from waiting to running? Let's say I was waiting for an IO event, the IO thing happened now. So why can't that process immediately run, right? And the answer is there's something else already running. So you can't just run this now that it's ready. So it has to go back into this queue and wait. And then when the scheduler decides that it's time for it to run, it'll run it. And finally, when things are done, it'll exit. Basically, it has finished running and its state becomes terminated, right? So now going back to this question, when the process is waiting to be assigned to a processor, which means that it has moved from this new to ready state. So the state is obviously ready. So when it's running, it's obviously not waiting for assignment to a processor. And when it's new, it still hasn't been admitted into the ready queue. So the answer here is ready. So any doubts on this? Any questions? Anything you want to know more about? I'll wait here for 30 seconds. No questions? Okay, then let's move to the next one. So, okay, this is kind of like a match the following. So you have 4 things on the left and 4 things on the right, and your options will be matching the left to the right. So let's look at the question. A process control block contains information associated with each process. match the information column with the relevant process column. So your first row on the left is memory management information. The next one is IO status information, accounting information, CPU scheduling information. On the right, you have priorities, memory allocated to processes, list of open files, clock time elapsed since the start. So I won't read out these options since it doesn't make much sense to read them out, but think of what is relevant with what. So is memory management have something to do with priorities, something to do with memory allocated, list of open files, clock time, and then try and match them. So this will take a bit of time, so I'll wait a whole minute and type your answers on chat. Any answers? Is this too confusing? So let's take it one at a time and see if you have answers. So let's talk about 1. Which of the right ones, PQRS, do you think matches 1? That must be simple. Any answers to that? Which of the following is memory management information? Okay, Q, memory allocated to processes. Fine. So what about IO status information? Which of the following is it? List of open files. Okay, R, list of open files. Great. So the third one, accounting information. Which of the following do you think it might match? So you have 2 things left, right? Priorities and clock time elapsed since start. Is that a bit confusing? Okay, P, priorities. Okay, CPU scheduling information. What do you think it is? So it has to be whatever is left out, assuming everyone agrees with this, right? So S, clock time elapsed since the start. So that makes the answer that you guys came up with as, which is it? Which of ABCD was it? So 1 was Q, QR. So let's see, 2 of these have QR, and then accounting you guys said was priorities. So I guess the option was C. Okay, does anyone think something else is the right answer other than C? And then we'll take a look at the answer. Let's look at the answer. So the answer is A, which means memory management to memory allocated was right. IO status to list of open files was right. Accounting information was clock time elapsed since start, and CPU scheduling information was priorities. So let's again look at this and see why you have this, right? Why? So I can clearly understand the confusion between these, right? So you might think that to schedule something, you need to know how much time has elapsed since the start, and you might have priorities as accounting information, which is fair enough. So let's look at this and see if that confusion goes away after looking at this. So this is a process control block. Basically, it holds everything that you need to know about a process. So first it has the state, which is all those things that we discussed, right? Running, waiting, ready, blah blah. Then you have things like the program counter, the CPU registers, right? All of this again we discussed is important for the state of a program. To bring it back into memory or to switch from one to the other, you need this. And next, coming to CPU scheduling information. So like the example that I was giving earlier, you have things like priorities for different processes. You might also have some scheduling queues, and you might have queue pointers to that. For instance, you have this ready queue, you have this IO queue. So you might have a pointer pointing to the front of the ready queue. You might have pointers for different queues like that. And for memory management information, you need to know about the memory allocated to the process. Basically, why is this, right? You need that process. So anytime you try to access memory that is outside the limits that are allocated to you, you will not be allowed to do that. So you can see here that there's memory limits, right? So every access to memory is checked, and this is one of the duties of the operating system, to provide you with that security. So basically, if you as a process are able to write to some other process's memory, then this notion of security and protection does not hold anymore, right? We don't have isolation between processes. So you can go and corrupt some other user's processes by simply writing some rubbish into their memory. So you should not be able to do this, right? So that's why the process control block maintains how much memory is allocated, what are the limits. So every access has to be within those limits, and if it's not, you'll immediately get an error. And then things about accounting information, things like the clock time elapsed since the start, the time limits. So so here's where, and the IO status information is basically the open files that the device has and devices that the process is using and things like that. So I think memory and IO, there was no confusion, so that's okay. So let's think about CPU scheduling and accounting, right? So the way I would think about this is, these are more generic things that might or might not be very relevant to scheduling. For instance, the clock time elapsed since the start, and that might not help you schedule. So you might have things like a timer which is set to this time slice, and once the timer expires, you know that okay, this process is now supposed to stop and the process will give up the CPU, right? So that is more in the sense of accounting. Whereas, so it's sort of general information that you need to maintain about the process, but CPU scheduling typically has these priorities, scheduling queue pointers and things like that. So this confusion is kind of valid. I understand why there is confusion, but it's just a matter of which category this falls into, right? So priority typically falls into scheduling because priority cannot be considered accounting information. Whereas the other option, which was clock time elapsed since start, may or may not be relevant to scheduling. So it's more general accounting information that you maintain about the process. So things like, so if you do PS, the command that I was talking about on Linux, you will actually see these values: CPU used, clock time since start, time limits. You'll see all of this. So try this out today and you'll see columns showing how much percentage of the CPU this particular process is using. It will also show you how long this process has been running, lot of other things depending on what options you use to display. So this is general accounting information that it maintains about a process. Whereas priority is typically very scheduling related. It's not used for anything else. So any questions or doubts here? I am assuming nothing. So let's move on. Okay, so a process does not give up the CPU under which of the following conditions? A, after a specific amount of time has elapsed on the timer, on IO request, when the stack memory is full, none of the above. Which do you think is the answer? And the question is, does not give up the CPU under which condition? Any guesses? Okay, A, after a specific time has elapsed on the timer. Okay, so process does not give up the CPU after a specific amount of time has elapsed. Any other answers? No? Okay, let's look at the answer. So the answer is when the stack memory is full. And let's again look at one of your scheduling slides to understand this better, right? So again, like I was talking about, what is the goal of scheduling? It is to maximize the use of your CPU and other resources on the system. And when does a process give up CPU? First thing, if you remember from this diagram, so when there is an IO event, it immediately goes from running to waiting, right? So then it gives up the CPU, and this is by design. So when a process is waiting for IO, it means that there is nothing for it to run. So why would you want it to be still running, right? So basically at that point, it gives up the CPU. That is one condition. The second condition is, let's say this is a compute bound process, and you would have heard of this IO bound, compute bound in your lecture, right? So compute bound is, let's say you're multiplying two matrices which are huge, right? So you have these computations running all the time. So that is a compute bound process, and that may not have an IO request at all. Maybe initially it takes in the data from the disk, and after that it's going on computing and computing and computing. So it never gives up the CPU because of IO. So in that case, how do you actually switch to the next process? So that is by means of this timer or time slicing that you would have heard of. So basically, let's say for now that this time slice is 10 seconds, right? So let's say your matrix multiplication program is continuing to execute, and then after 10 seconds the processor decides that okay, 10 seconds have elapsed, now this process will move to the ready queue and I'll execute something else. So and this when this 10 seconds happens, the process will give up the CPU. If not, you could have things where one process continues to run for infinity. So for instance, if you put a while one, right, and you keep it running, in the olden days it was possible to actually do that, put while one and then do that, and then it would just hog the system. But you can't do this when there are things like preemption and a timer, and it's by design. You don't want one process to keep running for eternity. You want other things to also get a chance, right? There is this notion of fairness, and later on in the course you'll hear about things like starvation, when one process does not get to run at all, right? So these are the two conditions under which the process gives up the CPU. When the stack memory is full, it will not give up the CPU. You might have errors. So for instance, a common error is stack overflow, right? And if you've done some really interesting programs, you might have seen this error. If not, I don't think so. And there is a way to actually go and in a C program to go and increase this stack limit in case you're doing something that's having a lot of that requires a lot more on space on the stack. There is a way to do that. So if you're curious, go look it up after class. But under this condition, it will not give up the CPU. It will basically error out. And after that, it might so happen that that process is terminated and something else is running, but it's not in the typical sense of giving up the CPU, as in moving from running to, let's say, ready or to waiting. It might go from running to terminated. So I hope that makes it clear. Any questions on this? Since we have 10 minutes left, I'll also ask again, do you have any doubts on the course content for this week 3 or maybe even week 1 and week 2, right? Something that you didn't clearly understand, something that you want further explanation. Please post questions on chat. Okay, if there is nothing, let's move on. So this is again a scheduling related question. The set of processes waiting for an IO device is maintained in job queue, device queue, ready queue, none of the above. So think about this. We already looked at this process state and that transition diagram, right? So if a process is waiting for an IO device, which queue would you put it in? Any answers? No answers? Does anyone think it's the ready queue? Okay, let's look at the answer then, if there are no other answers. So the answer is device queue, and let's go through these so that it's clear. So you have a bunch of these scheduling queues. Why do you need them? Because you might have multiple processes that are in a given state. So let's look at the state diagram again. So ready, right? Let's say you double click the Excel and then you double click your Chrome browser window. So now both of these are go from new to admitted because they're ready to be run on the processor, and you can have multiple of these. So then you would need some kind of data structure to store these, and it's typically a queue because you might be doing something like first come first serve. So you might say, you click this Excel button before Chrome, so Excel will open before Chrome, something like that, right? But you need some data structure to store all this list of things, and that's typically a queue. And so you need scheduling queues for this reason. So in all of these questions, it's not just about which option is the right thing, right? Think about it from a design perspective. Think about it as to why an operating system is designed this way. Why do you have all these things? What happens without them? That's really understanding operating systems better. So yeah, so this is why you need scheduling queues in the first place. So job queue is basically a set of everything in the system, all processes in the system. Ready queue is everything that is residing in main memory. So it's ready to execute, but it is not yet executing. And a device queue is basically a set of processes waiting for an IO device, right? So now going back to, so processes can go from one queue to the other. So let's say something is ready to be running and then it has an IO request. So let's take your Excel program again. So let's say first it's put into the job queue. It's also there in the ready queue because it's ready to be run now. And then let's say you say file save as and you do something. So it does an IO operation. So while it's waiting for that IO operation, it will be put into the device queue and it will no longer be in the ready queue because it's not yet ready to be running. And once this file save action onto your hard disk is completed, it will go back to the ready queue because it's again ready to be executing, right? So processes migrate among these various queues. Now I think this is pretty clear. Set of processes waiting for an IO device would be in the device queue. This is just a matter of terminology. But the higher level thing that you should keep in mind is this is a data structure that is needed for scheduling to happen. So any questions on this? I think we have 2 more questions, so I'll move quickly in case you don't have any questions. Anything that's not clear? Okay, let's go to the next question. So the degree of multi-programming is controlled by long-term scheduler, short-term scheduler, not any scheduler but the process itself, none of the above. Which do you think it is? Any answers? Okay, A, long-term scheduler. Okay, any other answers? A, great. Let's look at the answer. So yes, it is long-term scheduler. And again, let's take a quick recap about this short-term scheduler and long-term scheduler, right? So short-term scheduler basically selects which process should be executed next. So in going from this transition of ready to running, right? You have a bunch of jobs in the ready queue and one of them can run now, assuming you have a uniprocessor system. So you have only one processor and you can run one thing at a time, which is not the case. Again, if you're curious, for people who are very interested, you should go look up hyper-threading. So there is a way to run, say, 2 threads on one single processor. This is a feature that Intel offers. So if you have an Intel system, it will definitely support hyper-threading. So you can run 2 things at the same time. And it's interesting how that's done, but that's a bit advanced, so we won't go into that here. But usually the assumption is that if you have a uniprocessor system, you can only execute one thing at a time. And in moving something from ready to running, the short-term scheduler comes into play. So this is enough, right? So it might be the only scheduler in a system, and this is going to be invoked very frequently. So earlier I gave this example where the time slice was 10 seconds. So in reality it's never in seconds, right? It's milliseconds or microseconds, and so it will be invoked very frequently. So this scheduler needs to be fast because, for instance, imagine that you switch processes after every 10 milliseconds. And now suppose this scheduler takes 20 milliseconds to make a decision as to which process to run next. So that means that in every cycle that you do this, you're only spending 10 milliseconds on executing the program and 20 milliseconds on deciding which to execute next, which is really bad for the system, right? So what you want is something like you spend 9 milliseconds executing, you spend 1 millisecond deciding what to execute. And that's why this needs to be fast, because it's called an overhead, right? This is not something that's executing, it's deciding what to execute, right? So that should be fast. So this is a short-term scheduler. The long-term scheduler is not so frequently invoked, and it's an optional thing. It might or might not be there, and it decides which processes must be brought into the ready queue. And this controls the degree of multi-programming, which is basically how many processes can be there in the ready queue. And this is more used in the sense of what kind of mix of processes you have, right? Compute bound, IO bound, and you would like to have a mix of the two. If you have all compute bound processes, then the IO is going to sit idle, and there might be some processes which actually need IO, and you're not using your system resources well enough. So this kind of decides my degree of multi-programming, and the answer is long-term scheduler. So any doubts on this? Yeah, so the long-term scheduler drives for a good process mix, which is what I was talking about. No other answers, no other questions or doubts. Let's move to the next one then, since we are close to the end of the session. Yeah, so this answer was there on the last slide if you guys saw it. So IO bound process spends more time doing IO than computation with dash CPU bus, while CPU bound process spends more time doing computation with dash CPU bus. So many short, few very long, few very long, many short, few very long, few very long, many short. So I guess this might be a bit confusing, but let's see. What answers do you guys have? Any answers? Right, okay. So let's see if taking it one at a time makes it easy, right? So IO bound process spends more time doing IO than computation with dash CPU bus. So this is an IO bound process. It has a lot of IO. So it will do a lot of, it spends more time on the IO. So what kind of CPU burst do you think it will have? Many short, few very long. Those are the only two options. So which of these do you think it is? This is an easy way to get to questions when it's too confusing, right? Look at things one at a time. Okay, D is the answer. Okay, few very long. Okay, so for people who are still thinking about this, think about the second part of the question also, right? CPU bound process spends more time during doing computation with dash CPU bus. So split the question up and see if you can pick one option for this, one option for this. There are only two, and then you can pick the final option. Okay, so D and B are the two options I've gotten so far. Any other answers? Anyone who agrees with D? Anyone who agrees with B? Okay, I guess there's nothing else. So let's look at the answer. So the answer is C. So let's think about this. So you have an IO bound process, which means it has a lot of IO work. So it spends lot of time doing IO, but what are the nature of its CPU bursts? So every now and then it might have, so the two options you have for this are few very long and many short. And if you had few very long CPU bursts, it would no longer be IO bound. Very long CPU bursts means that you have a lot of work to do on the CPU, right? You have a lot of computation. So it can't be that. It has to be many short. So that means your options that are available are A and C. Then think about CPU bound processes. So now they spend more time doing computation with dash CPU bursts. So they don't have much IO activity. So why would it be many short, right? So if it's a short CPU burst, then it means that it has little bit of computation and then maybe IO, which is not the case for a CPU bound process. So it actually has few very long CPU bursts, and that's why the answer is C. So hope this is clear, and use this approach when you have confusing questions. Think about the first part, what is the answer to that? Think about the second part, then club it together. Any doubts on this? Okay, I'm guessing it's clear. Let's move to the last question and then wrap up. Okay, no doubts. Great. So the last question is about this process tree. So consider the following process tree. The process PID 8415, which is the second node on the left, will wait for which of the following process or processes to terminate? 8416, which is a child to it. Option B, 9268, which is a child of 8416, and 9204, which is again a child of this. PID equal to 1, which is the init process, which starts first in the system. Option D is 8416, 9268, 9204, basically all three. So which do you think it is? Any answers? So this process, the second node on the left subtree, will wait for which of the processes before it can terminate. Let's look at the answer then, if you guys don't know. So the answer is D, because the parent must wait for all the children to be terminated. So 8415's direct child is 8416, But the 8416 will in turn have to wait for 9268 and 9204, which are its children, right? So 8416 will wait for these two, and 8415 will wait for 8416, which means that associatively it ends up waiting for all three. So it has to wait for all these three to terminate. And the interesting part about this, why should it be this way? Think about that. So there are good examples of processes here. So you have init and then you have login. So init, let's say you boot up your system and init starts running, then you log into your system. Then you open up your shell and you do ps, right? Now, why should the bash shell wait for the ps to complete? What happens if it doesn't wait? And I'm not going to answer this. Think about this and then come back in the next session if you don't understand it. So for all of these questions, to understand the subject better, think about why something is in a particular way. Why is it designed that way? Can you do something else, right? That would really help you appreciate the design better, and it would also make operating systems more interesting. So most people have this thought that, oh, it's already been designed and there's nothing new to this, but there is a lot of interesting stuff that goes on in OS, and understanding these things a little better would give you that perspective. So any questions on this? We're already past time, so if there is nothing else, I'll wait to see if you have any general questions on the session. If you have any feedback for me, if you want me to include certain kinds of questions, you can put that also on chat. Okay, all good, great to hear that. So thank you for all the interaction. That really helps me take the session better, and thank you for coming to this week's session. Hope to see you in the next week. I'll wait a minute. If you have any doubts, you can hang back and post your questions in chat. If not, thank you for joining and you can leave the call. Okay, I'm guessing there are no further questions. So that's all for today then. Thank you so much.